We have observed that the incompleteness of theories underlying the design of interactive software makes it difficult to produce authoritative specific standards. As a result, the majority of design rules for interactive systems are suggestive and more general guidelines. Our concern in examining the wealth of available guidelines is in determining their capability to the various stages of design. The more abstract the guideline, the more it resembles the principles that we outlined in section 7.2, which would be most suited to requirements specification. The more specific the guideline, the more suited it is to detailed design. The guidelines can also be automated to some extent, providing a direct means for translating detailed design specifications into actual implementation. There are a vast amount of published guidelines for interactive system design. They are frequently referred to as guidelines for user interface design. We will present only a few examples here to demonstrate the content of guidelines in that vast literature. Several books and technical reports contain huge catalogs of guidelines. A classic example was a very general list compiled by Smith and Moiser in 1986 at Mitre Corporation and sponsored by Electronic Systems Division of the U.S. Air Force. The basic categories of Smith and Moiser guidelines are: number 1, data entry; number 2, data display; number 3, sequence control; number 4, user guidance; number 5, data transmission; and number 6, data protection. Each of these categories is further broken down into more specific subcategories which contain in the particular guidelines. Figure 7.2 provides an example of the information contained in the Smith and Moiser guidelines. A striking feature of this compendium of guidelines is the extensive cross-referencing within the catalog and citation to published work that supports each guideline. The Mitre Corporation has taken advantage of this structure and implemented the Smith and Moiser guidelines on hypertext system, which provides rapid traversal of the network of guidelines to investigate the cross-references and citations. Shown here in figure 7.2 are sample guidelines from Smith and Moiser, courtesy of the Mitre Corporation. Shown here in table 7.4 are the comparison of dialogue styles mentioned in the guidelines. Smith and Moiser contains question and answer, form filing, menu selection, function keys, command language, query language, natural language, graphic selection, while Mayhew contains question and answer, fill-in forms, menus, function keys, command language, natural language, and direct manipulation. A more recent, equally comprehensive catalog of general guidelines has been compiled by Mayhew, though this catalog is only in book form and so limits the possibility of quick cross-referencing. This is one of the best sources for the experimental results which back the specific guidelines. A major concern for all the general guidelines is the subject of dialogue styles, which, in the context of these guidelines, pertains to the means by which the user communicates input to the system, including how the system represents the communication device. Smith and Moiser identify each 8 different dialogue styles and Mayhew identifies 7. The only real difference is the absence of query languages in Mayhew's list, but we can consider a query language as a special case of a command language. These interface styles have been described in more detail in Chapter 3. Most guidelines are applicable for the implementation of any one of these dialogue styles in isolation. It is also important to consider the possibility of mixing dialogue styles in one application. In contrasting the action and language paradigms in Chapter 4, we concluded that it is not always the case that one paradigm wins over the other for all the tasks in application, and therefore, an application may want to mix the two paradigms. This equates to mixing of dialogue styles, a direct manipulation dialogue being suitable for the action paradigm and command language being suitable for the language paradigm. Mayhew provides guidelines and technique for deciding how to mix dialogue styles. In moving from abstract guidelines to more specific and automated ones, it is necessary to introduce assumptions about the computer platform on which the interactive system is designed. So for example, in Apple's Human Interface Guidelines, the Apple Desktop Interface, there is a clear distinction between the abstract guidelines, or principles, independent of the specific Macintosh hardware and software, and the concrete guidelines which assume them. The abstract guidelines provide the so-called philosophy of programming that Apple would like designers to adopt in programming applications for Macintosh. The more concrete guidelines are there seen are more concrete manifestations of that philosophy. As an example, one abstract principle espoused in Apple guidelines is consistency.
Golden rules and heuristics. A number of advocates of user-centered design have presented set of golden rules or heuristics. While these are, in a relatively broad brush, design rules which may not be always be applicable to every situation, they do provide a useful checklist or summary of the essence of the design advice. It is clear that any design following even these simple rules will produce a better system than one who ignores them. Netherman's 8 golden rules of interface design. First, strive for consistency in action, sequence layout, terminology, command, use, and so on. Number 2, enable frequent users to use shortcuts such as abbreviations, specialties, sequence, and macros to perform regular, familiar actions more quickly. Offer informative feedback for every user action at the level appropriate to magnitude of action. Number 4, design dialogues to yield closure so that the user knows when they have completed a task. Rule number 5, offer error prevention and simple error handling so that ideally users are prevented from making mistakes, and if they do, they are offered clear and informative instructions to enable them to recover. Rule number 6, permit easily reversal of actions. In order to relieve anxiety and encourage exploration, since the user knows that he can always return to the previous state. Rule number 7, support internal locus of control so that the user is in control of the system, which responds to his action. Rule number 8, reduce short-term memory load by keeping display simple, consolidating multiple page display, and providing time for learning action sequences. These rules are useful shorthanded for the more detailed sets of principles described earlier. Like those principles, they are not applicable to every eventually and need to be interpreted for each new situation. However, they are broadly used, and their application will only help most design projects. Norman's 7th principle for transforming difficult tasks into simple ones. Number 1, use both knowledge in the world and knowledge in the head. Number 2, simply the structure of tasks. Number 3, make things visible. Number 4, get the mappings right. Number 5, exploit the power of constraints. Number 6, design for error. Number 7, when all else fail, standardize. Norman's seventh principle provides a useful summary of his user-centered design philosophy, but the reader is encouraged to read the complete text of the design of everyday things to gain the full picture.
In chapter 7.6, we will tackle about HCI patterns. As we observed in chapter 4, one way to approach design is to learn from examples that have proven to be successful in the past, to reuse the knowledge of what made a system or paradigm successful. Patterns are an approach to capturing and reusing this knowledge of abstracting the essential details of successful design so that these can be applied again and again in new situations. Patterns originated in architecture, where they have been used successfully, and they are also widely used in software development to capture solutions to common programming problems. More recently, they have been used in interface and web design. A pattern is an invariant solution to a current problem within a specific context. Patterns address the problems that designers face by providing a solution statement. This is the best illustrated by example. Alexander, who initiated the pattern concept, proposes a pattern for house building called light on two sides of every room. The problem being addressed here is that when they have a choice, people will always gravitate to those rooms which have light on two sides, and leave the rooms which are lit only from one side unused and empty. The proposed solution is to provide natural light from two sides for every room. Locate each room so that it has outdoor space outside it on at least two sides, and then place windows in these outdoor walls so that natural light falls in every room from more than one direction. Note that the solution says nothing about where these windows should be located or at what angle they should be to each other. A room with windows on opposite walls or at right angles or with a window and a skylight would all fulfill the pattern. Patterns capture only invariant properties of good design, the common elements that hold between all instances of the solution. The specific implementation of the pattern will depend on the circumstance and the designer's creativity. The pattern also has references to other patterns, indicating both the context in which it can be applied, the top references, and the pattern that may be needed to complete it, the bottom references. This connects the pattern together into a language. Patterns in an isolation have limited use, but by traversing the hierarchy through these references, the user is assisted in generating a complete design. Patterns and pattern languages are characterized by a number of features, which taken as a whole distinguish them from one another. They capture design practice and embody knowledge about successful solutions. They come from practice rather than psychological theory. They capture the essential common properties of good design. They do not tell the designer how to do something but what needs to be done and why. They represent design knowledge and varying levels ranging from social and organizational issues through conceptual design to detailed widget design. They are not neutral but embody values within their rationale. Alexander's language clearly expresses his values about architecture. HCI patterns can express values about what is human or humane in interface design. The concept of a pattern language is generative and can therefore assist in development of complete design. They are generally intuitive and readable and can therefore be used for communication between all stakeholders. Patterns are a relatively recent addition to HCI representations, in which there are still many research issues to resolve. For instance, it is not clear how patterns can be identified or how languages should be structured to reflect the temporal concerns of interactions. However, the recent publication of a complete pattern language for web design aimed at commercial designers may mark a turning point and see a more widespread adoption of the approach in interface design.
Elements of Windows system. In earlier chapter, we have discussed the elements of the WIMP interface, but only with respect to how they enhance the interaction with the end user. Here we will describe more details of windowing system used to build the WIMP interface. The first important feature of windowing system is ability to provide programmer independence from the specific of the hardware at devices. A typical workstation will involve some visual display screen, a keyboard, and some pointing device such as a mouse. Any variety of these hardware devices can be used in any interact system, and they are all different in terms of the data they communicate and the commands that are used to instruct them. It is imperative to be able to program an application that will run on a wide range of devices. To do this, the programmer wants to direct commands to an abstract terminal, which understands a more generic language and can be translated to the language of many other specific devices. Besides making the programming task, the abstract terminal makes portability of application program possible. Only when the translation program or device driver needs to be written for a particular hardware device, and then any application program can access it. A given windowing system will have a fixed generic language for the abstract terminal, which is called its imaging model. The imaging models are sufficient to describe very arbitrary image. For efficiency reason, specific primitives are used to handle text image either as a specific pixel image or as more generic font definition. Example of imaging models: pixels. The display screen is representative as a series of columns and rows of point or pixel, which can be explicitly turned on or off or given a color. This is a common imaging model for personal computers, and it is also used by the X Windows system. Graphical kernel system, programming hierarchical interface to graphics, PostScript. Programming language developed by Adobe Corporation, which model the screen as a collection of paths which serve as infinitely thin boundaries or stencil, which can be filled in with various colors or texture patterns and image. Through these imaging models were initially defined to provide their abstract language for output only. They can serve at least a limited role for input as well. Example, the pixel model can be used to interpret input from a mouse in terms of the pixel coordinate system. If I would be the job of the application to process the input even further once it knows where in the image it occurred. We discussed the WIMP interface as an interaction paradigm in Chapter 4. We pointed out its ability to support several separate user tasks simultaneously. Windowing system provide this capability by sharing the resources. The Windows system must also provide the means of displaying the separate application. This is accomplished by dedicating a region of display screen to each active abstract terminal. In summary, we can see the role of windowing system depicted in Figure 8.1 as providing independence from the specific programming separate hardware device, management of multiple independent but simultaneously active applications. Architectures of windowing system. Bus and quotas identify three possible architectures for the software to implement the roles of windowing system. All of them assume that device drivers are separate from the application program. The first option is to implement and replicate the management of the multiple processes within each of the separate application. The option is to implement the management role within the kernel of the operating system, centralizing the management task by freeing it from the individual application. Third option provides the most portability, as the management function is written as a separate application in its own right. These are the example of application program. The client-server architecture support to manage the shared resources, so application built for a Windows system which is nationally based on the client-server model may not be portable as one would think. A classic example of Windows system based on the client-server architecture is the DAS3 Standard X system release 11, developed at the Massachusetts Institute of Technology in the mid-1980s. 8.3 showed the software architecture of X.X, as we mentioned earlier, is based on the pixel-based imaging model and assume that there is some pointing mechanism available.
Good day everyone, I'm RHEABEL Gonzales. I discussed the 8.3 Programming the Application. We now concentrate our attention on programming the actual interactive application, which would correspond to client in the client-server architecture of Figure 8.2. Interactive applications are generally user-driven in the sense that the action the application takes is determined by the input received from the users. Ito raw ay tinutugma sa client at server ng mga figure at ginagamit sa application. We describe two programming paradigms which can be used to organize the flow of control within the application. The windowing system does not necessarily determine which of these two paradigms is to be followed. Pinapakita dito ang dalawang paradigms na kung saan maaaring gamitin para maayos ang daloy ng control sa application. Read evaluation loop. Repeat. Read event, may event. Case, may event. Type. Type 1, do type 1 processing. Type 2, do type 2 processing. Client application. Start. Read input, process input, quit, and end. Server and device. The application has complete control over the processing of events that it receives. The downside is that the programmer must execute this control over every possible event that the client will receive, which could prove a very cumbersome task. On the Macintosh, this process can be aided somewhat by programming tools such as Mockup, which automate some of the tedium. At ang application ay nakumpleto na sa control at natatanggap na ito dahil ang client ay ang nakakatanggap.
Implementation support. There's two types of implementation support, the application and notifier. The application start, register callbacks with notifier, call notifier, process event. Then the notifier, read input, send to appropriate callback, callback request, or quit. In the figure 8.5, the notification-based programming control flows is centralized in the notifier, which relieves the application program of much of the tedium of processing every possible event passed to it by the Windows system. But this freedom from control does not come without a price. Suppose, for example, that the application program wanted to produce a preemptive dialog box, perhaps because it has detected an error and wants to obtain confirmation from the user before proceeding. The preemptive dialog effectively disregards all subsequent user action except for ones that it requires, say, selection by the user inside a certain region of the screen. To do this, in the read evaluation is fairly. Example of notification-based program. In figure 8.6 provides an example of notification-based programming in C using the X view. The program produces a window or frame with one button labeled quit, which when selected by the pointer device causes the program to quit, destroying the window. See figure 8.7 for the screen image produced by the sample program quit. 3 objects are created in this program: the outermost frame, a panel within that frame, and the bottom in the panel. The procedure xv_create used on lines 17, 22, and 23 in the source code of figure 8.6 is used by the application program to register the objects with the xview notifier. In the last instance, on line 23, the application programmer informs the notifier of the callback procedure to be invoked when the object, a button, is selected.